Alright, and I believe that we are live. What's going on, everybody? Welcome to the stream. Today we're going to be learning electronics. Alright, we're just going to be continuing to do an analysis of the circuit I was building on in the previous stream, except we're going to add some components this time around. Why did my music just get so quiet? Weird.
He was cast in Anna Karenina, and they were writing scenes. And he realized, if I'm going to do this and be on a horse, I have to do it for real. He injected himself into this scene every day for months.
I sort of took a crash course enough to get me through the movie.
Well, check. Mic check, 1, 2.
Hungarian national equestrian team during steeplechase. I was in the middle for a good reason. I was about to kill it and catch me on.
Okay, cool. Yeah, there's going to be some background noise, but whatever, you can get around that. Alright. Alright, so I have it drawn out here on paper. You can take a look at that, perhaps. So I'm just going to copy this over to the screen, over to the whiteboard, and then we're going to do an analysis looking at how much current and how much voltage I have at each part of the circuit. We're going to look at how the current splits at particular branches and in coordinates to Kirchhoff's junction rule, and then we're going to look at how the voltages equivalent to 0 in accordance to Kirchhoff's loop rule. So these are two important methods to analysis when it comes to linear circuits and shit like this. So let's get into it. I'm going to start drawing it. I'm going to draw it best I can. I kind of suck with this pad though.
My dad was competing in a cross-country horseback riding competition.
I really do want to do a good job. So get it straight on so that my lines are straight and shit. Maybe get the mic a bit closer to me so it's a bit louder. I'm like moving the whole table. Okay. This ought to do it. Separate it. Okay.
That was the last time I saw his feet.
Rumors have it flying since 42-year-old Christopher Reed fell off a horse this past weekend. Well, tonight, many of the worst reports are true.
Okay, and if you're unfamiliar with any symbols regarding electronic components, I'll begin to specify each component. Okay, so this is a battery, and a battery typically consists of I had to sneeze. A battery consists of individual cells, so if you were to see some sort of symbol that was just like this, that's a battery. More than typically, that'd be 1.5 volts, because each cell of a battery is 1.5 volts. And so if we're looking to analyze a 9-volt battery, really a 9-volt battery is a combination of, what, 4 1.5 volt cells. Wait, no, sorry. 1.5, that's gonna be 2. Wait, that shit don't add up right.
Horror show. It wasn't clear what was going to happen. His doctor not impressed. This is not encouraging. Mr. Reed currently has no movement or spontaneous respiration. He may require surgery to stabilize the upper spine in the near future.
5, 15, 4.5. So that's 3 of them, 6. It'd be 6 cells. It'd be 6 cells, right? Because let's do the math. 3 times 1, that's gonna be 3. 3 times 5, that's 15. Which is gonna be 4.5. Yeah, so 6 cells. 6 cells. So this battery here really consists of 6 1.5 volt cells. Okay, but we're just gonna draw with only 2 cells like this. I mean, it's I think that's typical. That's typically how it's done. But again, this is a battery. Fuck, man. I really drawed it like shit, though. I really have an issue with that. I absolutely hate it. I draw so well on paper, and then coming to this thing, it just looks like absolute left pocket dog shit, so. But again, the battery, it's going to have a large plate on top of a small plate, large plate on top of a small plate. The small plates are essentially the negatives. So it's like we have these cells in series, right? And when you put things in series, even if you put batteries in series, you're going to get an addition or a sum of voltage. So if I had two 9-volt batteries in series, I'm gonna have 18 volts. If they're in parallel, you just get if they're in parallel, which looks like this here. So let's specify the difference between series and parallel. This will also be very important when doing circuit analysis. So let's say we have this 1.5 volt cell. This is parallel. The negatives are connected and the positives are connected. So that's what parallel looks like. And then this is in series. The positive is connected directly to the negative of the other battery. And so, can you see that? Here, I'll put it in a different position. That's a bad spot. Okay, so now, this is very, here, let me draw it out first. This is very important when doing analysis. We'll keep that 1.5 for the purpose of understanding. 5 volts. Say 1.5 volts. 1.5 volts. Okay, and then we're going to specify. Whoops. Oh, great.
This break is what happens when the trap door opens and the new snatch tight. Half an inch to the left, it is half an inch to the right. An embarrassing.
I think that's how you spell parallel. No? Fuck. I don't even know how to spell parallel, my boy. Yeah, that's correct. Okay. I knew I had it. I knew I had that. Never second guess myself. Ever. Okay, so that's parallel, and then this one is, where can we see that on screen? Right here. Series. Okay, so parallel and series. And now when you have you have batteries in parallel, and this goes for any component, they act in a particular way, okay? If we're talking about resistors, resistors act in similar ways to batteries in regards to their orientation, such as series or parallel. You really only have these two, okay? Okay, so for regarding orientations of components, you only have these two. They're either in series or they're either in parallel, okay? And so when we're talking about batteries, they kind of act similar, as in when you have them in parallel, it manipulates the current. If you have them in series, it manipulates the voltage. And resistors, which look like this is the symbol of a resistor, right? We just got this squiggly line here. That's the symbol of a resistor. I guess we'll specify here too. I don't know. I could have drew this way better. I don't have none of this planned out. I'm just winging it, so let's fucking do it. I'm gonna continue. So to have a resistor in parallel or in series manipulates the specific. I don't know what you really consider it, but I'm just saying that if you have a resistor in parallel, it too manipulates the current. If you have resistors in series, it too manipulates the voltage. If you have a capacitor, which looks like this, we'll do a polar capacitor, which means it does have a positive and negative side respectively. This is a capacitor, the symbol for a capacitor. Okay, so if you have a capacitor like this, it acts differently than the resistor and the batteries. If you have capacitors in parallel, it manipulates the voltage. If you have capacitors in series, I just want to make sure.
Marsha became my mom's best friend and was like a sort of fairy godmother to me.
Shit. I don't want to skip a beat. Let's not even dive into capacitors though. Again, I didn't have this planned out. I'm just kind of winging it. So let's not confuse and dive into capacitors, but let's stick with these basics right here. Because this is pretty much all that our circuit today is going to consist of, is things like this. Okay, so again, it's important to understand. And so when you have batteries in parallel, you're increasing the life of the current. So instead of 1 amp hour, you get 2 amp hours. Okay? And so which means you can run, you can supply 1 amp for 2 hours. Rather than if you have only one battery, you can only supply 1 amp for 1 hour. And then as you, like, if you were to supply 0.5 amps to the circuit or draw 0.5 amps from the circuit, with one battery it would be 2 hours. With 2 batteries, you could supply 0.5 amps for 4 hours. Okay, so it works in this way. Now when you add the batteries in series like this, you have 1.5 volts plus the other 1.5 volts, so you get a total of 3 volts. So you just have an addition of the voltage when you have them in series. When you have them in parallel, you increase the you don't increase the current, because the current is dependent upon what the resistance of the load, but you are capable of supplying the same current for a longer amount of time when you have batteries in parallel. If that makes sense. I hope that makes sense. Okay. And now resistors. Let's look at resistor networks. Some simple ones, and let's assess this real quick to get an understanding. So we'll look at resistors in parallel.
John Houseman had just won the Academy Award for Best Supporting Actor. So it was really very important to have a serious classical actor.
Nope. Okay, resistors in parallel. Resistors in parallel. Okay, so now to quantify it, let's just give it a battery as well. Let's draw a simple circuit. And again, those are resistor symbols. We'll just call this R1, R2, and this is our battery, 1.5 volts. Okay, resistors in parallel, we'll go to resistors in series. Resistors. In series, resistors in series. And again, R1, R2. Okay. Okay, so again, when you have resistors in parallel, they're going to manipulate the current. When you have resistors in series, they're going to manipulate the voltage. So this is a voltage dividing circuits. Does my writing look good? Does it please you? Okay, and then a current. a current dividing circuit. Okay, so we have 1.5 volts, we have R1, we have R2, and down here we also have 1.5 volts, we have R1, R2. Okay, let's entertain the scenario where the resistances are the same magnitude, and so let's just consider it to be 220 ohms. Wait, I'm gonna write it like this. I'm going to say that, wait, for everything. So I'm gonna put it off to the side because both of these circuits, R1 equals R2, which equals 220 ohms, which is a common resistance value. Okay, so if R1 equals R2, which equals 220 ohms, we have both resistances at the same magnitude. Okay, we'll write the equation out here then. So, okay, we'll look at a simple method of Kirchhoff's loop rule. Man, I guess, I don't know, I'm just running through a whole lesson. We were going to do my circuit, but I guess these are the basics, and so for you guys to be on the same, like, or at least a level playing field, it's necessary to understand these sort of things. So I guess let's run through it regardless. I'm just gonna check Twitter and see what's happening. Check X. What's the quality like? Is it looking good? Quality? Why is my... It's at 240 pixels, like just standard, automatically. I have the ability to change it all the way to 1080. Yeah, that looks good. Alright, man. It's all good. Hey, what's up, y'all? I appreciate y'all being in here. I'm on YouTube too. I think I'm live on YouTube as well, which I have to actually be like careful of what I say if I'm streaming on YouTube. Perhaps not, considering how small my channel is, but maybe they'll still get me. Maybe they still get you for some shit. Live right now. I probably have no viewers on YouTube though. I get most of my views from X. It says one watching, but I think that's probably for me, huh? I'm just gonna leave it running then. I guess with one watching, it might lead to another. Alright, whatever. Okay, so... Gosh, I feel like I could just do this so much more clean, but we've already started, already initiated the process. Let's continue, proceed forward. Okay, so to analyze this, there's a couple methods. Okay, so you can either use Kirchhoff's loop rule or... I don't know, I'm going to show you another method to do this. So let's start with Kirchhoff's loop rule though. And Kirchhoff's loop rule says that the sum of voltages around any closed loop is going to equivalent to 0. So this is what this looks like in regards to this particular circuit. It's going to be like 1.5 volts minus R1 times I1, which is going to be the current drawn by these two resistors. And because these resistors are in series, they're going to each experience their own voltage, although they're going to experience the same current. And the reason is because, like I said earlier, if you have resistors in parallel, they manipulate the current. If you have them in series, they manipulate the voltage. If they're in series and manipulating the voltage, they experience the same current. If they're in parallel and manipulating the current, they're going to experience the same voltage. I had to think about that one for a second. Yo, I hope y'all aren't confused because I almost got myself confused. But alright, so these both are experiencing the same current, so we can say that I1 flows through this entire circuit. It's consistent, okay? Okay, minus R2, which just so happens to be the same value as R1, so I mean we could say R1, right? But we're going to say R2 because we're going to specify, because it might not always be the same value of resistance, although it's always the same current. And now this, according to Kirchhoff's rule, equals 0, okay? Okay, so now we have our value of 220 ohms, and so for this we can solve for I1. Okay, so let's see what that looks like. So 1.5 minus 220 I1 minus 220 I1. Now this is going to require some basic algebra. I mean, surely, I don't know, surely you're capable of doing this. Okay, so we're going to move 1.5 to the other side. Actually, let's move the 220 to the other side because it's a negative. So we're going to have 1.5 equals, we're going to pull it out to, so 220, or pull the I out, no, because they're the same value. So we can just call it 440, actually, 440, because they're both going to be an addition, 440 I1. And so 1.5 divided by 440, I1 equals, you know, yeah, forget that actually. I'm gonna get my good calculator out. I'm gonna put my phone away. I don't want that. Okay, so 1.5 divided by 440, and that's gonna equivalent to 3.4 milliamps, approximately. Okay, 3.4 milliamps. Yeah, so that's the current. And now to figure out the voltage across each resistor, you would just take the current, which is consistent throughout the circuit, and multiply it by the magnitude of the resistance. And this is because, this is expressed in Ohm's law. So let's write that down too. And I've wrote this down in several different videos, but it's it's a necessity. It's something you absolutely need to know when doing electronics. So Ohm's law. Ohm's law, okay, and this looks like this. Voltage equals current multiplied by resistance. And so now we figured out the current through some basic algebra and by using Kirchhoff's loop rule. And so now we just take 3.4 milliamps multiplied by 220 ohms. And that's exactly what we have here. We have a current multiplied by resistance, and this is going to give us a voltage across the resistor now. So mind you, this is only across the resistor. So, it's the voltage from here, here. And then again, we're going to have a voltage drop from here, here. And it's going to be equivalent because we have an equivalent resistance. So it's going to be the same. So if we were to do that, okay, so 0.0034 times 220, and that's going to be 0.748. Okay, wait, now that times 2, okay. So again, these are approximations because I'm not writing it down to 16 decimal places, so it's going to equivalent to 0.748 volts. Okay, and so that's our voltage drop across the resistors, or across the one resistor, and then since it's equivalent resistance on the other one, it's going to be the same voltage drop. And now if you were to take that 0.748 times 2, you would see that it equates to 1.496 volts, which is close enough to 1.5. As I said, I wasn't carrying it all the way, or all the decimal places. And so you can see that if you have the same magnitude of resistance, that you're just going to split the voltage into 2. And that goes for however many resistors you add of the same value. So if I had 4 resistors of 220 ohms, I'd have an equivalent voltage drop across each of them, and it would be to where that each voltage drop summed to 1.5 volts. Like a conservation of energy type shit. Okay, so let's look at what happens in a parallel circuit. Okay, so again, we're manipulating the current, and so the voltage remains constant across these parallel resistors. So I have 1.5 volts across this resistor and 1.5 volts across this resistor. So regarding recalling Ohm's law, it's as simple as if it's 220 ohms, I'm going to have, here's my current flowing in this direction from positive to negative. Just 1.5 volts divided by 220 ohms, and you're just going to have 6.8 milliamps.
I like making sense of people. I do. But I'm also
6.8 milliamps. And again, because they're the same magnitude of resistance, this is what you're going to have in both of them. And again, the voltage is constant across them. Okay, and so according to Kirchhoff's junction rule, the current being drawn from the battery is going to be the sum of these two currents that split off at this junction. This is the junction here. You see that there's one direction in this way and then one direction in this way. And now to really to determine a junction, you can see that each component from the point of that junction goes directly to ground. You know, to the negative side of my battery. So it goes directly from positive to negative. Whereas these two, you have one side of the resistor connected to the other. Okay, and this is what determines series compared to parallel. And this is how you determine a junction. Okay, so keep that in mind. Okay, and now as I was saying, the current being drawn from the battery is the sum of these two. So really, we're going to have 6.8 times 2. We're going to have 13.6 milliamps being drawn from the battery. In total, whereas in this circuit, we literally only have 3.4 milliamps being drawn from the battery because it's constant. When you have resistors in series, the current is constant. Okay, so very important to know Ohm's law, very important to understand the difference between series and parallel, and then very important to understand Kirchhoff's junction rule and Kirchhoff's loop rule. Alright, yeah. That's kind of what you need to know right now. I guess I could cover how transistors work a little bit, but maybe I'll do that once we get to that point. As of right now, let's start to draw the circuit that I need to control the display of my voltage supply. We are currently building the circuit that will control the display of my voltage supply, which will indicate the amount of voltage I am supplying at the current time. If that makes sense. If that makes sense. It was good, it was good. Damn, what do I got here? Interesting. Interesting. I don't know how to No, I genuinely don't know how to gain viewers. Let's see. I'm gonna try to send it to a community and see if I can get people to join. I'm gonna say learn. Don't watch me teach electronics. I hope I don't get kicked out of the community for this, because I'm kind of promoting myself. But we'll see. I mean, I think it'd be beneficial to people in the community, but shit, you always get those. Perhaps you get sticklers and shit. I don't want that. Dope. What's up, everybody? I appreciate y'all coming in and joining. Okay, we're gonna start drawing Okay. Okay, we're gonna start drawing this circuit out now. Again, I'm gonna do my best, but I'm not very good with this Intuos pad. It kind of looks like shit, but we'll see. Let's see what I'm capable of doing. Okay, we're also going to be dealing with a potentiometer because the potentiometer itself is what's going to vary the voltage of my voltage supply, but at the same time, it's also what's going to determine which transistors of my display control circuit will turn on and off. So those will be governed by the turn of the potentiometer. And now a potentiometer is drawn in a particular way, but I'm gonna modify it just a little bit because it gives a better analysis. It gives a way better analysis. I'm gonna draw it as if it's consists of two resistors, which it kind of does, but really it's typically drawn as just an arrow and one resistor. But you'll see. I'm gonna draw it like this. Again, bear with me with my squiggles and shit, man. I'm trying to draw straight. Fuck, that looks like ass.
We were talking earlier about the potential power vacuum that this is creating. Just a few moments ago, Syrian Turkey-based opposition leader telling Al Jazeera TV that
Got news on right now talking about Syrian government.
Arab countries to agree on
A lot of crazy shit going on right now, man. Okay. And also, I've problem solved this circuit in a way that uses a relay, but I 100% can use transistors and use some sort of logic, like a and or not gates or whatever the shit. But I'm not very knowledgeable in the logic yet. I'm not very knowledgeable in those logics and the orientation of the transistors to get the and or nor whatever. But shit, man, that's something I really do want to get into because that's how computers work. They work off of all that transistor logic, and that's how you convert your binary from binary into actual logic on the computer. You know what I mean? So 1, 2, 3, 4. I only need 4 resistors here. Yeah, that's great. Oh yeah, it looks great. Looks like fucking shit. Okay, there we go. Looks a lot better. See, how did I even get that bomb? How did that just happen? I was drawn straight. That's some bullshit. Okay, and again, this is my potentiometer. Okay, so up here we're going to do a voltage dividing circuit for the purpose of supplying my LEDs. And so as of right now, I'm going to use an 8-bit LED segment display. I think that's what you would call it. But for now, That's what I'm going to use for the indicator of my supplied voltage for my voltage supply. But right now I'm just going to light up LEDs because it's just going to be much easier when doing this like prototype design before I do the actual circuit. And so again, as we discussed earlier about the voltage dividing circuit, because I have a 9-volt battery and I need to drop it down to 5 volts for these LEDs. And we're going to do that through a voltage dividing circuit. Okay, and another another necessity of symbols is the ground symbol, because it's not always pleasant to try to connect all the grounds when drawing the schematic or the diagram, so you can just easily use this ground symbol, but in reality all the grounds are connected, so every one of these symbols are actually connected to each other, which is all connected to the ground of the battery, the negative side. Okay. Now, okay, and so this too is a voltage dividing circuit, which is in series with this potentiometer, which is a variable resistor. And so now when I vary the resistance of the potentiometer, it's going to vary the voltage across this entire circuit. And so I'm going to be varying the voltages across each resistor. And so when that happens, and I reach a certain level of voltage, I'm going to have a particular magnitude of current flowing through these resistors here, which is going to activate when I want them to activate the gates or the base of my transistors, which will close the circuit to the LEDs and light them up and supply them. So now I'm adding these resistors for the purpose of determining the amount of, or determining when I want them to turn on, because you'll have a voltage across this resistor which dependent upon this resistance here will draw the desired amount of current and activate the gate to the transistor. So I'll explain that better. I'm not really sure if I need a resistor here, but anyways, we can consider these like current limiting resistors. Current limiting. And this is what a transistor looks like. Symbol for a transistor. Oh, that was a really bad circle. It's a really bad circle. That's an acceptable oval. Right. Okay. Nope, ain't gonna do that. I'm gonna redraw it to make it smoother. Ain't gonna do it. That's good. But yeah, like, brother, what's going on in Syria right now? Truly, I mean, I don't know. I see Yeah, I see Candace Owens post things about pray for the Christians in Syria, and so I will say my prayers tonight. But I don't know. I haven't done enough research. I was thinking that there's a possibility to do some research tonight and share that research with you guys, but I don't know. Perhaps we'll just stay out of politics and I'll just continue to do the electronics for now. Oh, okay.
No, stop it.
Wow. Am I still streaming? Whoa. What the? What? What's going on with X right now? Huh, I'm still live on YouTube. My X isn't loading. This is okay. Bro, am I still live? Okay, good, I'm still live. Oh my goodness. Every time I went into it, it just kept telling me retry and reload. It wasn't working. But yo, what's going on, everybody? Yo, I really appreciate you guys being here. We're just doing some circuit analysis. This is a control circuit for the display of my voltage supply, or it will be. Still messing around with the idea. I mean, you guys are here learning with me as I'm learning, or I guess practicing. So, we can do this together if you guys have any interest in building electronics or anything. But I don't know, even if not, it's good knowledge because this is like the foundation to everything that we have. Okay, I mean, all of our tools, our phones, every piece of technology. It's the modern age. So, interesting stuff. Perhaps applicable, perhaps not. Perhaps you're here for the entertainment, trying to be funny, trying not. But yeah, I don't know. Whatever's going on in Syria, bro. Pray for the Christians. It's really messed up. I don't know why this war just continues on and on. I don't even know for what purpose they're fighting for. I haven't done my research, but again, let's get back into it. Okay, so things are looking good. I think I'm getting better with the Intuos pad. My drawings are looking a little bit better. So again, I need to do more research into the logic of transistors because I know this is accomplishable in that way. But since I don't really understand that, I'm just going to use a relay in a particular manner. You'll see here. And I'll try to make it make sense. This is the symbol for a relay. And the way the relay acts is that, I guess let me do it like this. Is that this side here is always closed until you activate the coil here, and then it's going to switch to this side. So, what I want to do is I'm going to ground, which is, it's kind of really like the input to the relay, but we're going to use it in a different way, and I think it should work. I mean, according, I think it should work. I don't know that it is going to work, but I think it should. And so we're going to ground this. No, 100% will work. 100% will work. It absolutely makes sense. Okay, and so there's that, and he's connected to that. Okay. So this is what it looks like, and then this is my LED. And you know, wait, here, let's actually, an LED I think looks like a diode. It's the same symbol for a diode. So let's actually draw that correctly. Whereas I'm just kind of drawing like a light bulb, like something to mimic a light bulb. But symbol for LED. Let's actually see what this looks like. I want to draw it correctly. Okay. This is what it looks like. And plus, it's probably going to look way nicer to draw. Yeah, so it's just like a diode, because it's a light emitting diode. LED, that's what it stands for. So it literally just looks like this. Oh yeah, look at my straight line. Really? Fuck out of here. Fucking shit keeps popping up. Bro, oh my god. What? Bro, I keep going to the right. I keep drifting to the right as if I have no control over my hand movement. And they got like arrows like this. Oh my god. Oh my god. I can't fucking draw that small. Oh shit, it's gonna piss me off. Fuck, I don't like any of it, and it keeps fucking deleting more than I even wanted to. Those are my arrows. Oh yeah. Oh shit. Okay. Good enough? Is that good enough? Does it look like the symbol to an LED? Here, look. This is what it looked like. Good enough? You know, I actually do got an idea, actually. It would be a lot better. There. Just fucking zoom in a little bit, bud. Japan, okay, I don't give a shit. Quit popping up. There, this You guys ever listen to Audio Slave? That shit kind of hits. Chris Cornell, he's a great singer. Fuck, I hate. Oh my god, bro, it keeps popping up. There, that's better. There, that's better. Gorgeous. Best LED I ever seen. and I only seen it once. Want to make sure we're live. Huh. Hey, what's good? I appreciate everybody being in here. Cool. Very cool, very cool, very cool. Bro, no. Wait, I'm still live. Come on. Oh, okay, never mind. Okay, cool, 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 cool. Alright, bet, let's proceed. Okay, now we have to draw another LED. I always spend so much time drawing this shit out. Like, I gotta get to the analysis part. There's so much to analyze here. And I really need to figure out how to implement matrices into my analysis, bro. I need to figure out how to use that in correspondence to Kirchhoff's loop and Kirchhoff's junction rule and all this stuff. It's absolutely necessary. Alright, let's zoom out again. Kind of move him over here. Oh yeah, we can ground him up here. He's gonna be grounded. Okay, and that's the ground symbol. Okay, so this here is going to run to another transistor and going to activate another branch of light, just like this. Circle it up. Yeah, he's gonna run there. Shit. 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 Okay, so there's dots on this thing that run vertically, horizontally. It's like a grid of dots, and I'm following the dot precisely, and it looks like that. It looks like that. Like how? I'm following the dots. I'm following the grid. I'm following a straight line, and it looked like that. I don't know, something about it is very wrong. Something about that is very fucking wrong. I like alter the thickness of this. Yeah. That's better. Oh yeah, that's great. I can also do that too. That's gonna be, maybe that's better. It just doesn't always work every time. I gotta like fight it. That time worked. Cool. That's beautiful. See if I get straight lines like that. That looks great. Phenomenal. And he's gonna be connected there. So see, if you didn't want to do the ground symbols like that, then you'd have to do some jumps like this, like I'm going to do now. Watch this. Which I think it looks like shit. Be like that. See, it didn't work that time. That straight line shit. Good enough. Straight line? Cool. Good enough. And then again, we have another LED here. Straight line? Cool. Good enough. Just like that, like that, like that, like like that, something like that. Cool. Beautiful. Okay, again, our relay, or the input of the relay is connected to ground because this switch is going to be closed. And so now at the beginning of the circuit, so now at this point, okay, this is a voltage dividing circuit. And so from here to ground, which is this point, so we'll just call this point A. A, B, C, and then just ground. Okay, so point A to ground across all these resistors is going to have the highest voltage. Point B will have a slightly lower voltage. Point C will have the lowest voltage drop across this one resistor. So now at point A, with the highest voltage of this voltage dividing network, I'm going to have a high voltage, and this resistor being in parallel to all of these resistors will experience the same voltage, and depending on what the resistance is, the magnitude of the resistance will determine the current running through it. But again, this resistor is in parallel with these three, and so it experiences the same voltage with a current running through it determined by the magnitude of resistance. And the same goes for these, but we are dropping a resistor every time. So now this resistor here experiences the same voltage as these two, and again this resistor here experiences the same voltage as this one. And so now we're going to do an analysis of the voltage drops, and we're going to determine the amount of resistance we need to get a current which will activate the gate of our transistor, which on the data sheet it specifies it's 10 milliamps. Maybe that's a maximum. I'm not sure. It says 10 milliamps, but I activated the transistor with as little as like 3 milliamps. So we're gonna stick with that. We're gonna use 3 milliamps as a guide. That's what I'm gonna say activates the transistor is 3 milliamps. So that's what we use. Yeah, I can learn some electronics. I mean, who knows? Maybe you'll need to build some shit in opposition to the government. I mean, who really knows? But yo, what's good? I really appreciate everybody being in here. Let's go. I don't know, let's build some shit. If you guys are working on any projects, let's go. Let's do it. I want to see it. Send it to me. DM me. I want to see your projects. Alright, let's continue. Okay, and so the thing with okay, so yeah, so this will be the first one to activate, the first transistor to activate, which will obviously activate this LED, or allow the supply from right here to even get to the LED, which the LEDs also require a current of 20 milliamps. For green LEDs, and then I think it increases with the color of the LED. It depends, but 20 milliamps is what is going to be what we're working with. Because we're going to need to know that to do our analysis into, like, we need to know some, we have to have some knowns. If we know absolutely nothing, then we're just fucked. Okay, so we have to have some knowns, whether it's resistance values, whether it's voltage values, or whether it's current values. We have to know something in order to find our unknowns, which we have a lot of unknowns right now. We have a lot of unknown resistor values, but I do know current values that I require because these certain components have specifications, and they can only operate with particular magnitudes of current or voltage, depending on what it is. So those will be our knowns. It's pretty much our current and our voltages, and then we'll have to find our resistances will be our unknowns. And we're gonna do this through Ohm's law, Kirchhoff's loop rule, Kirchhoff's junction rule. I thought I said one more thing earlier too, but I don't know. That's pretty much it. That's pretty much it. And then here again, since I got more people in here now, I appreciate y'all being here. I'm just gonna show you this one more time because this is something we covered earlier. And that was an earlier design of when I was really trying to work this out. But since then I've upgraded. I have a much better understanding. So, but this is really important, and this was just like a quick lesson into the difference between having components in parallel and in series. Okay, and then we covered Ohm's law, and then this is like a this was an example of Kirchhoff's loop rule, and then this was an example of Kirchhoff's junction rule, and then how you get a split of current at a junction, and then how the voltages or the voltage drop across each component in a closed loop equivalates to 0, and that's exactly what we proved here. So those are very important things when doing circuit analysis or building circuits. You gotta know that shit, man. You gotta know that stuff. So again, Ohm's law, Kirchhoff's loop rule, Kirchhoff's junction rule. Okay, proceeding forward. You know, I'd really like to play my music for you guys. I know I can on Rumble. I probably can on X, maybe. I don't know. I always get copyright violations on YouTube. And I'm streaming on YouTube right now, but you know what? Fuck YouTube. Said it. I said it. Whatever. My channel's too small. They ain't gonna do shit, bro. They don't even know about me. They don't even know you, little bro. But, alright, this is where we are. And so now we can, like, denote everything. I mean, you know, all of these resistors are going to be denoted by R, and then we just specify R1, R2, R3, whatever the fuck. Transistors are denoted by Q, so it'll be like Q1, Q2. Relays, oh, actually, since we already used R, I don't know, we can, like, use the, what would you call it? Nah, it wouldn't be considered nomenclature, would it? I know what nomenclature in chemistry is, you know, but nomenclature in regards to other things, I don't know. But anyways, the relay, we're just gonna use L, which is the denotation, or the notation, not denotation. It's just the notation for inductors, and that's exactly what we pretty much have. We have, you know, this inductor here that's operating the lever of the switch. Bada boom, bada bing. And that actually requires 120 milliamps to operate. So, you know, we can begin to add these values in here now. So I need a current of 120 milliamps in this direction. I don't know. I guess we can find out when we get there, but I don't know how that's going to work. Because no, that should work. That should work out fine. Yeah. Okay, here I'm going to need I don't know, like I said, we're just gonna use 3 milliamps because when I tested it, it was only 3 milliamps to operate the gates of the transistor, so 3 milliamps. 3 milliamps. Again, 3 milliamps, but these are going to activate at different turns of the potentiometer. This will be the first to activate, this will be the second to activate, this will be the third to activate, but really I want these two to activate at a similar time because this is going to switch from grounding this LED to grounding this LED because I want this LED to, determined by the turn of the potentiometer, I want this LED to turn off and this LED to turn on. And I guess this is the way I've decided to do it. I don't know, this is what makes sense to me. I'm sure there's more optimal ways or perhaps not. Perhaps I found a more optimal way, but again, if I knew how to do the logic with multiple transistors like the AND, NOR, whatever, fuck, I gotta do some research, read up on that. I saved a book that I think somebody posted on X, and I saved that book like a, you know, an ebook online. And I really do have to study it because it was talking about using logic gates in, I think like microcontrollers and shit, which are absolutely vital to robotics. And I really want to start building some robots, and some drones and stuff, bro. I really want to. I think it'd be a profitable business to get into as well. Profitable industry. There's a lot of opportunity, a lot of potential. I mean, it's undoubtedly the future. It is the future. So, you know, I'm really glad that y'all can be here to learn with me if you're interested in doing this stuff, because it is undoubtedly the future. Although I know there's a lot of simulations that can help in circuit analysis and circuit design, but to TBH, I'm so unfamiliar with them. I'm super unfamiliar with any simulators. So just doing it by hand, you feel? Okay, so 3 milliamps, 120 milliamps is what's going to be necessary. Now for these LEDs, 20 milliamps. Now, also something I want to express is that we have very particular values of resistors. Like some values are 68 ohms, 47 ohms, 100 ohms, 150 ohms, 220 ohms. So now when I'm writing down like 20 milliamps, 3 milliamps, 120 milliamps, granted, I don't really want to go any less than those. It's okay to have a little more. But obviously can't too much. But these are like perfect values. These are perfect values, which are probably unachievable. But as long as I'm within range and a small tolerance, it'll be okay. It'll be okay. And that's gonna be that's reality when it comes to it. Not even the 68 ohm resistor is actually 68 ohms, and it's gonna vary from resistor to resistor just by like, you know, small tolerances. So nothing's perfect, but these are just values to shoot for, you know. Aim small, miss small. Okay. Aim big, you're gonna miss big. So let's aim small. Alright. But this is what we're shooting for. In an ideal world, we would have exactly 20 milliamps, we would have exactly 3 milliamps, whatever. But not even the LEDs or the transistors themselves are perfect, so it's okay to be imperfect, alright? Everything's gonna be alright. Okay. Alright. I don't know, we can start labeling these R1, R2. And I actually know what these are gonna be. Okay, so again, back to series and parallel. Look at this resistor and this resistor. Resistor. We need the current there. I don't think that's necessary, you know? But I guess that would 100% determine that. Maybe we'll keep it there. Wasn't that giving me an issue before? No. No, I'm trying to think. So these two resistors are in series. And so we're gonna get it's a voltage dividing circuit. So we're gonna have a voltage drop across him and a voltage drop across him. These two resistors are in parallel with the battery. So that means that this entire thing here, from here to here, is also receiving 9 volts. 9 volts. I wanna get rid of those lines. Okay. So now that's important because we can go ahead and analyze that that branch. We can analyze that right now. Actually, let's just start with that. I don't know, I guess this is my method of analysis. Watch and witness. This is how I'm gonna do it. Okay, so 100% need 5 volts across him. So 5 volts across him. We're just gonna draw it like this. Hopefully that's clean and you understand 5 volts. And so we have 9 volts total. So in order to get a 5 volt drop across this resistor, I need to drop 4 volts here. Okay. All right, because 4 plus 5 is 9. Okay. You get it? Okay, but boom, voltage drop of 4 volts and the voltage drop of 5 volts here. And then we're gonna have a break off. Okay, and so now the current through this resistor is going to be equivalent, or is going to be the sum of the current through this resistor and the current through this resistor. And we already know that that's 20 milliamps. The current through this resistor really can be anything. Obviously, it can't exceed. Okay, so it's 5 volts. I have half watt resistors. And so now this is like a power rule. Okay, power is in the units of watts. So here's the power equation. I don't know if this is also considered Ohm's law or like a part of Ohm's law. I'm not really sure. But the power equals the voltage multiplied by the current. And so if I have a half watt resistor and I have 5 volts, through algebra we can determine the current. I don't know. Okay, 0.1. Okay, I don't know. Maybe I'm an idiot for not being able to do that real quick. 0.1 amps is the maximum current we can have, and that's 100 milliamps. Okay, so that's the maximum current that we're capable of running through a half watt resistor that has a voltage drop of 5 volts across it. Okay, and really you don't even want to do that. You don't want to run it at its maximum. You never want to do that. I mean, it would probably burn up. I think there is a rule pertaining to this. I don't know. I'm not familiar enough. I don't know what it is, but we're just gonna keep it way low. We're gonna keep it way below that. Okay. So what now? Okay. So now we've determined that I need 5 volts across here, 4 volts across here. Is what I want to do. Yeah. 5 volts? Yeah, let's keep it at 5 volts. I don't know, I could say 6 volts. Should we do it? Let's change it to 6 and 3. Let's change it to 6 and 3. For the purpose of any imperfections, perhaps I want to have a little more voltage disposable. So 6 and 3 is going to be our ratio. Okay. So now 20 milliamps. 20 milliamps. So whatever, we'll just run 40 milliamps into this portion of the circuit. 40 milliamps. Want to be true, and then 20 milliamps here. Okay, so I guess we can determine our value of resistance. Let's see how this works out. Through Ohm's law, which again, Ohm's law is voltage equals the current multiplied by the resistance. And again, you can manipulate this algebraically in any way that you want to. So with that being said, if we have 3 volts divided by 0.04 amps, we're gonna have 75 ohms. Let's see how this pans out. So 75. Yes. Okay, and then 6 divided by 6 divided by 0.02 is going to be 300 ohms. And so at 300 ohms with a 6 volt drop, we're gonna have 20 milliamps running here. I guess I already drew an arrow. then that will leave us with another 20 milliamps at our disposal. So that's why I don't want this. Oops. I don't want that resistor. I'm just gonna run it like this. Bro, oh my gosh. It just won't do it. It won't straighten up for me now.
I really have no idea what this thing is or does or what it's worth. You know, to me it looks like
You know what? I'm done with it. That's it. Fuck it. Alright. That's my line. Okay, there it is. 3 milliamps. Okay, and this one resistor, so like this is the way that the potentiometer works, is that it has one part of it. Okay, so if it's a 1 kilo ohm potentiometer, this one varies from 0 to 1 kilo ohm. But this one is a constant 1 kilo ohms, which is directly in parallel to the battery. So that means that this is going to have 9 volts across it. And so a 9 volt drop across a 1 kilo ohm resistor is going to be 9 divided by 1000, and that's going to give us 9 milliamps. Okay, but we're gonna want to, okay, so like 9 divided by 100. I mean, we could go even smaller. I don't know that I have any smaller potentiometers than 100 ohms, so let's just roll with that. But again, as we increase the resistance, we're gonna get a smaller current. As we decrease the resistance, we're going to get a larger current. I need to make sure that I have a small enough resistance to get a current that's greater than, excuse me, that's greater than 126 milliamps at least. You know, in regards to 3 milliamps plus 3 milliamps, 6 milliamps plus 120 milliamps, that's 126 milliamps. So I need that at least. So I just don't think I'm not going to be able to accomplish 120 milliamps. It's just not going to happen. It's going to be too low of a resistance. Shit, I think I just found a problem with the circuit. I just found a big problem. Even 100 ohms only gives me 90 milliamps when 9 volts across it, and I'm not even gonna have 9 volts. It's not gonna happen. Ah, shit. Oh, okay. It's going to be another transistor that activates the relay. That's what it would be. So it'd be like, okay, I know how that's gonna go. It'd be like this, guys. So not 120 milliamps, but Okay, yeah, so we're gonna use this transistor, and once this is activated, it will supply the relay with 9 volts, which will 100% activate it, and I will get my 120 milliamps that I need. This will work. This will work. Now I can easily get my magnitude of resistance. I can easily get my current needed and a good magnitude of resistance. It's within possibility now. It's within possibility. I love when shit comes together. Let's see what's happening on X. I want to see what you guys are up to. Oh no, I got 10% on my phone. You guys listen to Rage Against the Machine? Cool. What's good? Michael Jordan numbers on here. 23. I appreciate y'all being here. Hope you guys are learning something. I hope I can help teach you something. Most definitely progressing together. I have a lot to learn as well. I have a lot of room to grow. But this is what we're here for, right? This is what we're doing. We're practicing and we're doing these exercises and we're getting more familiar with these laws and the way, the operation of the components and things like this. Okay, so let's see. What's a good value for a potentiometer? Because now, let's see. What do we want? I want 333. So I need at least 9 milliamps. Easy. So let's just burn. I wonder what are those values going to be. Does that even matter? I don't know if it matters. Let's burn I don't know what, 20 milliamps. Let's just run 20 milliamps. Alright, let's just run 20 milliamps. And then we'll just get rid of the rest. Not incredibly efficient, but I just want to get the operation. I just want this circuit to operate how I want it to. And then feel satisfied and then dwell on my success. I think that's what we're going for. Alright, but anyways, I'm already bored. What's a good value? Let's see. To get 20 milliamps, what? No, I don't know that necessarily. Get like that. 20 milliamps. Maybe, perhaps have to start further back. 3. Well, if it's 20, then it's gonna be like 20 milliamps minus 3. So right here, it's going to be 17. I'm not gonna write the unit. 17 minus another 3, it's going to be 14. Minus another 3, yeah, and then 11. Going the distance. He's going in for speed. Yeah. So that's what it's gonna look like. Because again, according to Kirchhoff's junction rule, the current through this resistor and the current through this resistor, or the current through this resistor is the sum of these two currents. Because at every junction is split. Kirchhoff's junction rule. Okay, but 20 milliamps through here, 20 milliamps through here. So how can we determine my voltages? I'm trying to think of the best way to analyze this. He's going the distance. He's going for speed. don't know. I guess it's kind of up to me when to activate. So it'd be best to determine how quickly the potentiometer changes from 0 to 9 volts. I don't know, like let's just activate with every change, or well, 4 resistors. Three resistors. Three.
Let's take a look here. All the glass, total value was about everybody's happy.
Yeah, I think we'd want them all to be the same value, I think, at least as far as for resistance. So, alright, let's just play with this idea then. So, okay, so, 4. So let's say we have a 2.25 voltage drop across each of these 4 resistors, because that equates to 9 volts. Wait, it'd have to be 5 though. Oh, I guess it'd be. Yeah, let's say 5. Okay, so what's 9 divided by 5? 1.8 voltage drop across each of these resistors. Well, if that's true, what's 1.8 divided by 0.02? 90. That's close enough to 100. Okay, so but that's the thing. That's the thing when you have shit like the potentiometer. It almost fucks with me. It's like because it's going to be varying the resistance, and so I have to look at it in like multiple states. So if I have 3 points of activation, I think we want to, if we have a 100 ohm resistor, we want to look at it when it's at 33 ohms. No, we'll just go like 30, 60, 90. So at its highest resistance, yeah, and that's when he'll activate. So at its highest resistance. Okay. Okay. At 90 ohms, it's gonna have 1.8 voltage drop across it. 1.8. And again, 1.8, 1.8, 1.8, 1.8. But what is that? No. Wait, yeah, what is that? 1.8. 7.2. Fuck. Fuck. I gotta see. I don't know, I gotta hook this up. I gotta hook the potentiometer up. What do I have in here now? 501. Oh, fuck. I gotta go get all my components. Shit, man. What's good? What's good? What's good? What's good? Let's see what's going on next. What's up? I appreciate everybody being here for real. Hey, yo, give me a follow. Drop a like. I don't know. Whatever the fuck you guys do, man. I'm gonna continue to make content. I'm gonna be more consistent. Like, let's do it. Let's learn together. Follow me if you enjoy this stuff. If you want to build your own stuff. Yeah, let's do it. Okay, okay, we gotta get this down though. I'm a bit frustrated right now. Because like the whole potentiometer is just, for whatever reason, is fucking with me. For whatever reason, I have a hard time grasping the concept. Like it makes me feel like an idiot. Okay, because it's gonna have different states. And so at maximum resistance, I mean, really, it's gonna be 100 ohms. Okay, fine. Let's use a 100 ohm potentiometer. Okay, so at this state, it's at its maximum resistance of 100 ohms, which means it's pulling as much current as it possibly can, or as much voltage as it possibly can. As a greater voltage drop, 100 ohms. I don't think I want that though. But it doesn't actually go to 0. Okay, so this is why. Here, let me. I gotta do a test. I'm gonna just see this. I'm pull it apart. I'm done with it. I'm getting rid of all this. Bitch. Drop the mic, bitch. Transistor. I'm not gonna drop him. I'm gonna set him right there. I'm gonna set this other transistor right here. Oh, oh man, I lost the potentiometer. Oh, there it is. Okay. Potentiometer? Yes, sir. Okay, the problem with this is I think this is a 1 kilo ohm potentiometer. I gotta go get my components. I'll be right back. Alright, boom. Resistor pack. Okay, let's see. Oh. There's a 500 ohm resistor. Okay. Now, why 500 ohms though? I mean, because I know I did pick that for a particular reason. No, that's fine. No, I want 100 ohm. I want 100 ohm. That's why. No. Okay, there's something I gotta understand. I gotta get a better understanding of this. Know what I mean? Cool, I'm glad I have so much space on my desk. I'm glad I have enough space to do my work. I don't got enough space. Know what I mean? Yo, for real, guys, also follow me on X, bruv. I'm gonna be posting more content. I'm gonna be building stuff. I'll be working on hydroponics. So for real, give me a follow. Wow. But regardless, I really appreciate y'all being here. I'm glad you can. You can see I have it pinned, my most recent hydroponics design. You can see I have it pinned on my X profile. So perhaps take a look at that. I was currently growing mescaline mix. Right now I'm in the process of germinating jalapenos and lemon balm, which I'm not really familiar with what lemon balm is. was a herb or something. But okay, what I need to see right now is what I get from the output of the potentiometer as I vary it in resistance. While it's supplied by a 9-volt battery. One other thing I need to look up so I don't get it wrong, because I got it wrong before and burnt a couple out, is the pinout, which is like my connections. I'll show it on screen also. Pin out of potentiometer. That's perfect. That's exactly what I'm looking for. Alright, I just gotta find the right one. That's what mine look like. Whew. I guess I'll show you this now. We just gotta find mine. Oh, I found it. Boom! So that's what we're dealing with. VCC output ground. Okay, I fucked that up bad before. Okay, and again we got our 9-volt battery. The only other thing I need is a multimeter. Okay. Multimeter, and I want to be reading the voltage, so I'm going to set it to 20 volts DC, direct current. Right here, I got my connector for my battery. VCC, what is the input? Yes. Okay, this just fell out of my breadboard like it was fucking nothing. That's not good. That's not how it's meant to be, but okay. Just like that. VCC's on the right side. Grounded on the left. Okay, and my shit's falling. Another thing I need is a flathead screwdriver so that I can turn the potentiometer, because it does not get a knob on it. So we're gonna bust out our handy dandy. I got everything you need. It's like genuinely for electronics, I think. Yeah. Electronics repair kit. That's what it's called. Alright, so we're gonna get this flathead here. Alright. Connect this up. Alright. And another thing I need are my alligator clips. I have no idea where they are though. I guess, is this just going to tell me the voltage across this? So 0 volts to 8 volts. 0 to 8 volts. Okay. 0 to 8 volts. And now, what does my battery measure? 8 volts. That's not even what I want to measure. That's not what I want to measure. No, what I want to measure is I want to go to the resistance setting. Yeah, that's what I want to measure. So we're going to go to the 200 ohm resistance measure, and then I'm going to connect it to the output positive to the ground, just like that. This is, well, and so, yeah, okay, okay. Yeah, literally from 0 to 100. Okay, no, I'm good, I'm good, I'm good. Okay. Yeah, so I was kind of on the right track earlier when I was saying that we need to split it into, since we have 3 points of concern. 3 points of concern. What was I thinking of? Shit. Oh, I kind of lost my train of thought. Okay, yeah, so 3 points of concern. At 100 ohms, this is also 100 ohms. That motherfucker gets hot quick. Wait, whoops. Oh yeah, wait, what's the watt rating of these potentiometers? 101 potentiometer. Power rating of of 101 potentiometer. It's 0.5 watt. The potentiometer has a maximum current of 100 milliamps. Okay. 100. Oh. The power rating of a P101 potentiometer is 0.5 watts. And the potentiometer has a maximum current of 100 milliamps. I guess that makes sense. I'm pushing 90 milliamps, but I'm not even close to 0.5 watts, and it's getting really fucking hot. Right? 9 divided by 100. Oh, wait a second. Oh, well, in that scenario, that's not going to be the scenario. That's not the case. Okay, never mind. That makes sense. Okay. I think I got this. Alright, so we over here. Okay, so we're going to look at different circumstances. So, initially, we're going to want the highest. The highest. And then. Yeah, right, because he is gonna be like, shit. Shit, hey, what's good, everybody? Yo, I appreciate y'all being here. Damn it. Okay. I gotta conclude better and come to a better conclusion. Fuck, I'm real tired. I want to go to bed, but I gotta conclude better. Since I got you guys in here, shit, I gotta take, advantage of the opportunity. I appreciate y'all being here, so. Alright, let's do it. But this is the point that we've come to now, doing our analysis. I figured out, right? Yeah, I figured out what resistance I need here. I just need to figure out the resistance of these. To determine the resistance of these will be very easy. So this voltage dividing network, for whatever reason, is giving me trouble. What I need is like, okay, so I don't know why it's so tricky. It's because I don't understand it. It's tricky because I don't understand it.
Okay.
Mm-mm-mm.
This guy is irradiated or something. This is for your fireplace, maybe a radiant heat. Or maybe it just looks pretty. Man, I hate when I find stuff I don't know what it is. Because then I'm able to go find out what it is. Like I'm with this.
Yeah, so I need 20 milliamps. Wait, so 20, in order to have 20, I need 9 divided by 0.02. So that means I would need a total resistance of 450 ohms in this box. A total resistance of 450 ohms. And that's including these. We gotta remember that these resistors are in parallel with these resistors, dependent on where it is in the network. So we're gonna keep that in mind as well. Excuse me. Okay, yeah, 450 ohms. That's doable. We could do more than 20 milliamps and have a, or no, it starts to be less if we want a higher resistance. So this is what we'll work with, which is fine. So I have 100 ohms there. Which okay, so if this is at 100 ohms and I want 20 milliamps, then this is going to have a 2 volt drop across it. And then as that decreases, well, I'm not going to maintain 20 milliamps, right? No. What is going to happen as I decrease it? The resistance in the network is going to change. The total resistance from 450. That's what's going to happen. So now it's going to be 9 divided by. So if we change it, let's just say no. We want like 60. Yeah, we'll say 60. So if it's at 60 ohms, we have 9 divided by what? We were originally at 450, right? 450 ohms. Okay, so what I'm saying is that in order to get 20 milliamps running through this entire circuit, I need a total resistance of 9 divided by 450 ohms equals 20 milliamps. So now if I decrease the potentiometer to 60 ohms, I'm going to have a total resistance of 390 ohms. So now 9 divided by 390 is 23 milliamps. And so 20 milliamps, that's going to be, alright, it's going to be lower, and then we're going to have 23 milliamps, it's going to be higher. Yeah, higher. I just need to contemplate these stages. I need to understand the stages. 390 equals 23 milliamps. Again, approximations. And then let's get rid of another 30. So divided by 360, 25 milliamps. It's all pretty close. 0.0. Oh, whoops, what the fuck? 360 equals 25 milliamps. And then, another. Wait, what the fuck? The first time I subtracted 60. Why do I do that shit, bro? 60. No, because I was just supposed to do 30. Oh my god. Wait. By threes. Fuck. Here, we'll make it make sense. And that's going to be fuck you. I want to write it like that. Oh, didn't mean to do that. 20 milliamps. 20 milliamps. Okay, let's subtract, what, there's fucking, so there's three stages, so 450, no, but it's not like that, it's, just 100. Yeah. Okay, so 457, this is how I'm gonna do that, okay. 383, 350, 9 divided by, and now this is like turning the potentiometer by a third every time. So this is at the maximum resistance of the potentiometer, turn down by a third, turn down by another third, and then right, turn down by the last third. Wait, wait, no. Yeah, 33, so, yeah. Bro, I'm fucking trippy. Oh my goodness. Maybe I do need to go to bed. I keep fucking up. I don't want to confuse you guys. Holy shit, my math ain't mathing, man. I went out on the dunes today, though. Maybe I'll post a video on X. Shit was lit. Got some razors, Polaris razors. Okay, 9 divided by 4, 17 equals 9 divided by 4, 17 minus 33. 3, 8, 4 equals, and so it's 1, 2, one more minus 33. This will be the last one. So really, this is the resistance that the voltage dividing network needs to equivalent to. 351. Okay, so 9 divided by 4, 17. This is our changes in current. It was actually not huge, and that's really good. 9 divided by 3, 4, 23 milliamps. 9 divided by 351, 25 milliamps. More like 26, but whatever. Okay, so this is how our current's going to vary in the circuit as I change the value of my potentiometer by a third. Right, because that's 1, 2, and that's the last one. It'll be 0. Yeah, and that's 100 right there. That's a difference of 100. Just about. It's really 99, but you feel. Okay. So now it's at a maximum, and this is when I want this will be initiated. So 20 milliamps. We also have 20 milliamps through him, and then I have 3 milliamps going in this direction. 20 milliamps, 3 milliamps.
I mean, at first I thought it was just a regular, like, silk t-shirt. Yeah. But I couldn't figure out where you put the picture.
Shit, okay. You know what? I really appreciate you guys being here. I really appreciate you guys being here for real. I don't know, I'm really working on this live streaming thing. I want to get better. I feel like this live stream was much better this time around. The introduction to this live stream began by doing like very simple analysis and describing how, or the difference between having components in series and parallel. And those are very important things to understand. Again, so is Ohm's law, and so is Kirchhoff's loop rule, Kirchhoff's junction rule. So I'm going to post this to Rumble, but then also you could replay it on X and everything. I will stream tomorrow, and I'm going to continue from here and finish up the analysis and then perhaps build it. I'm not positive, but right now, bro, I'm just super tired. I don't know. I can't, like, I keep fucking up. I'm just mad tired right now. I really appreciate you guys being here, bro. Give me a follow. I'm gonna continue to create content like this. I really do plan on building things in the future too. Like, I developed one time an electrolysis reactor, and I really do want to like hone in on that. I really like the chemical reactors. I want to design more of that. I really am interested in like manufacturing and production. So, um, currently I'm studying electromagnetic induction in my physics textbook, and I totally want to bring you guys along with that too to do my studies and stuff. I've just kind of been absent from that from some time now, but in regards to the electromagnetic induction and doing my studies there in that field of physics, I want to build a induction heater. And obviously this requires circuit work, and we can do the physics, we can theorize and put it on paper, figure out our magnitudes, like our magnetic fields and stuff like this, and do it for the experience, the knowledge, and all that stuff. So I do want to build that, which will require circuits as well, and that's kind of like the engineering aspect more than the theoretical physics. I don't know, it's all just really fun and beautiful, but I really need to put in some more work and really fucking, I just want to do it because I want to, produce technology. I want to build technology, and I want to develop it. I want to lead in the developing of technologies, but I really need that experience. And if I can bring you guys along with me, then how beautiful would that be? So let's do it then. I'm going to live stream my progress, and I hope that you join me. Give me a follow, like this stream. Again, you can watch it on Rumble. I'm going to upload it tonight. And then tomorrow I'm going to stream, and we're going to continue from here. But for real, thank you for being here, guys. And God bless you all. God bless you all. I really like to end my stream now, but my mouse isn't anywhere to be seen. Bro, what the fuck, bro? And look at it, stuck right there. It's because of this.